the capacitance value. Okay, so now we come to the formula for parallel plate capacitor. Okay, parallel plate capacitor. So first we redraw the same thing again, like what we did just now. This is our parallel plate capacitor. Another one here. One here. Okay, and then we assume that the separation is D connected to positive and negative terminal, and the surface area is A. Okay, now let's assume at the moment we don't put anything in between. Okay, we don't put anything in between. So based on the formula is this, the capacitance of this formula is actually directly proportional to the size of the surface area. Okay, so the bigger the surface area, the more charge you can store, the more electric field you can set up in between that parallel plate. So that's number one. And then it is inversely proportional to the D. The closer you can make it, the closer you can actually put them together, the larger is the stronger is the electric field, and of course the larger is the capacitance. So when we combine both of them, we get this directly proportional to A over D, and when we form equation, we have a very special value in front. Okay, so this value here is called K, Ka over D. And what is K? K is actually the dielectric constant. Okay, the dielectric constant for the material you use. Okay, for the material you use. So our K here is actually quite simple as well, where the K is actually equal to epsilon R, epsilon naught. It depends on two things. Now we're going to look into further what is epsilon naught. You already know the epsilon naught. The epsilon naught is the permittivity of vacuum, which is 8.85 10 to the power negative 12 farad per meter. Remember this? That's why it's connected to farad. Okay, and then your epsilon R, this one is called relative permittivity. Okay, relative permittivity, and this one is the permittivity of vacuum. Okay, permittivity of vacuum. This one is relative permittivity, meaning that this relative permittivity, it is a number that shows how good is that material use or the insulator use in conveying the energy of electric field relative to vacuum. Okay, so because of these two, our formula, okay, in general, okay, our formula in general, the capacitance formula become epsilon R, epsilon naught A over D. See, that is our formula. If you look at the formula, it's all based on the geometry of the design and also the nature of the constant. For example, this one is a surface area of the plate you use. This is the distance, the separation between the plate you use. This one is the constant, which we can find some other methods. Epsilon R can be measured, okay, by using some other method. Example of the R. Okay, example of R, we look at a few material here that we know of. This is the material. This is the epsilon R. For example, vacuum. We know it's 1.00. And then for A, it's also quite close, 1.00. And then for water, it is 80.0. That means if you put water in between them, your capacitor have 80 times the ability to store charge compared to vacuum and air. Okay, and then you can have like rubber, synthetic or natural, maybe somewhere between 3 to 5. And then mica is a type of insulator. electric insulator and also heat insulator. This is about, I think is 3.7, somewhere like that. So there are much more than that. Normally the value will be given to you if you are asked to calculate. So see, we have the formula now, but the formula of the A can be square, it can be rectangle, it can be circular, okay, it can be a circular shape. Any shape that you already know the formula how to calculate their surface area, but normally is square, rectangle or circle. All right, okay, so that is the formula for our parallel plate capacitor. All right, so the next one is example on how to use this equation. Okay, our page number 3, example on how to use the parallel plate capacitor formula. Now let's assume a parallel plate capacitor has circular plates, okay, has circular plates of radius, let's say 18.0 centimeter. If they are separated by 45 mm distance, calculate the capacitance if A, the space between them is vacuum, then the space between them is let's say water, just for fun of it lah. Okay, so there are two medium used. Okay, two medium used. So our first one, A, we know the formula is this one, epsilon r epsilon naught A over D. All right, now our epsilon r for vacuum we know is 1, and epsilon naught is of course this one. And then the surface area is what? Pi times 0.18 square. Oh, sorry, just the 1 square only. Pi r square. Like that. And then the separation is 45 mm. 45 mm is the change of meter, which is -3. So this one we're going to get 8.85. 10 minus 12 multiply pi and multiply 0.18 square, divide by 45 minus 3. Okay, we have this 2.0 10 to the power -11 farad. Okay, that's number 1. Then B, our C, so we use this one, C for CV for vacuum, this one in water, epsilon r epsilon naught A over D. Now if you look carefully, epsilon naught A over D are the same, so we actually can take them out. This one, the whole thing is CV. Okay, CV. So if you know the vacuum value of the capacitor, then you can calculate the rest by multiplying the epsilon r. Of course, for water we know it's 80 times, so 80 times 2.0 10 to the power -11, so this is what we get, times 80. So now you're going to get 1.60 10 to the power -9 farad. Okay, so 80 times because you put water in between. Okay, but do we really use water in your capacitor? Not very likely, unless it is for research purposes, because by putting water in there, I don't think it's a good idea, because once you use your handphone, suddenly it leak out, your whole handphone come out with a lot of water, computer flooded and so on. Well, that is just for theoretical calculation. Is it possible? Yes, possible. Is it reasonable? I don't think so. Alright, so wait for the next video on capacitor network and also energy in capacitor. Alright.